Hello, everybody, and welcome to session number 12 of my lecture on statistical energy analysis and hybrid methods. This time we come back to the system idea. So from all the wave treatments of fluid and structural waves, it's time to deal with continuous systems that are created out of some structures or some fluid cavities, and we start with the fluid systems. Until now, as mentioned before, all our wave propagation treatments had something to do with unbounded media. So it was an infinite fluid, semi-infinite fluid, infinite plate or whatever. And this will end now because now we will deal with bounded things. So as mentioned in the introduction, we will come back to the system approach, and now we start with fluid system. So what that system means as a system approach, that we will have some kind of excitation. It could be a source strength, and we will get a system response, typically a pressure signal somewhere in the room or whatever in the system that we are describing. So to get a system, we need some boundary, some surrounding. So we need a bounded system, and it could be a closed cavity, it could be a tube or whatever. And in this cavity, we will have input functions or signals. It could be whatever velocity at the wall. It could be a source excitation, a source strength, a volume source, and we have some responses here somewhere in the room as pressure. So the idea is to understand what is the physics and the dynamics of such systems. So what is the typical behavior of such systems? And we start with, and maybe not start with it, we will just talk about academic systems like rooms or tubes, because this is something that we can calculate without using very complex numerical methods to calculate them. Good. As mentioned, we start with a very simple one. It will be just a fluid tube. So a very thin air layer of fluid, which is characterized by the impedance, which is consisting of the density of the fluid and the speed of sound, and the damping loss factor. So the arrangement here is as follows. We have some left-hand side properties. We have velocity at the boundary. We have the pressure, which is the left and the right-hand side of this fluid tube, and we have the same situation here at the end of the tube at the length Lx. The solution should be quite well known. So this is our famous one-dimensional wave solution of the one-dimensional wave equation. We have two propagating waves, one in forward direction with amplitude A and one in backward direction with amplitude B. From this automatically follows the velocity. It's the derivative of the pressure, and the relationship between pressure and velocity is given by the, as you know, by the characteristic impedance. And we have a negative value here for the back running wave. That would mean another velocity. Good. So we have now everything on board to solve this for specific inputs. And in the first step, we assume that the interaction just takes place at the beginning and the end of the tube. And so this is something that we would call a two-DOF system, as it was also treated in the early sessions of my lecture. There's only one critical thing to understand. We have to separate a little bit between internal and external quantities. So when we talk about the pressure, as it is mentioned here in the solution, which is the pressure here inside the tube, it has we have to consider a different pressure when we think about the pressure on the right-hand side here, because just imagine a positive pressure at this side would lead to a negative velocity, and will be a different case for the left-hand side pressure here. So we have to juggle a little bit with the signs of our solution. That means when we're talking about pressure 2, which is an external pressure, that corresponds to the negative value of the left part of the pressure here at Lx, or it is equal to the right part of the pressure here at Lx. So that means we have to use another value for if we talk about external pressure here. Good. So that's what I said and mentioned. As an external pressure, we have to consider the right-hand side pressure here at the end of the tube, which is the negative value of the pressure as it would occur here in this solution. So once we have clarified this, the solution is quite simple. So we just use the results at x at 0 or xLx, and then we would get those expression from the second equation here for the velocity. When we take the difference of both equations and multiply by the following exponential functions, we would exactly create the solutions for A and B. And this was the only unknown components in our given equation. And when we enter this into the pressure formulation, then we get this expression for pressure 1 and at x equal to 0, and we get this for the pressure 2, which is again the negative external pressure, and we would get this expression. So now we have here all the velocities. We have our pressure formulation, so now we have everything that we would need to write this in matrix form, and this would look like this. So this is the matrix equation for pressure excitation when we are interested in the velocity response of our two-DOF system, considering a tube, or some people also call it the transmission line. So far, so good. Yeah, as already said. So when we would like to have another expression, so that means that we're now interested in some situation where the velocity is excitation, that's quite simple. We just have to invert the matrix shown on the last slide, and then we would get this expression here after the inversion process. Good. For later studies, we would like to have a look into the pressure field and the velocity inside the tube. And for doing this, we are using the related constants A and B, which follow from all our solutions. And then we get the following pressure field here. Just to remember that this is A and B. This is the positive and negative propagating wave, and we get a different relationship, slightly different relationship for the velocity, but just the characteristic impedance is missing here, obviously, because it's divided by the characteristic impedance. Good. We will use this heavily when I will get into the details of random systems, because that's an excellent playground, because it's a simple solution. We can run thousands of experiments and do a lot of statistical study without heavy numerical pain. Good. Next step is now to give you some typical responses and what is the typical behavior of such continuous systems or tube system. So in the first step, we take an even simpler system. So we will switch from 2-DOF to 1-DOF. This is easily done by just replacing the relationship between the pressure and the velocity at the second part on the right-hand side of the tube by just defining an impedance. So which is the characteristic impedance Z2, and that's the negative pressure divided by the velocity. If we enter this in our solution for pressure 1 in the matrix equation, then we get this pressure response for a given velocity, which would look like this. From this, we can easily, okay, now we have those values here. We see that this is the boundary condition at the second n, and we start with the very simple case, which is the rigid boundary condition. So we assume that the second impedance is much, much bigger than the characteristic impedance. and this is meaning actually a rigid boundary or a stiff end of our tube, or a hard wall, some people say. If we enter this here in the above equation, we get this typical tangential relationship. So the pressure is a characteristic impedance by velocity divided by the tangents of wave number times the length of the tube. And here, when we just would like to calculate the radiation impedance from this, which is quite easy, we just have to divide by the velocity, then we get the following impedance formulation for the left input in the tube. K here is a complex damping, because when we defined the tube, we had assumed damping loss factor, and this is considered by introducing a complex wave number. When we have a look into the impedance solution, we see a very typical shape. We see the lot of spikes here for the real part and the imaginary part. And obviously this is related to resonances at here in this low frequency solution, which occur for length when the length is equal to an integer number of half lambda. This is, for instance, one option, so you have lots of spikes. But if we look into the higher frequency domain, we have another effect. So what is happening? So again, we have a deterministic behavior until KLX is in the order of magnitude of 1. So here in this regime, typical deterministic behavior. But for the high frequency behavior, we have something where the imaginary part goes to 0 and the real part equals exactly the characteristic impedance of R. What is happening there? We will later explain this in detail, but a very heuristic explanation of this is the following. In our solution, we have positive and negatively propagating waves. And due to damping in the high frequency, the reflected part is no longer there. So that means for high frequency, our continuous system behaves as a free field. So in the high frequency, all the resonances and all the reflections, or effectively the second boundary is no longer existing. This is a very important thing in SEA, because when SEA subsystems are coupled, they are always considered as a kind of semi-infinite system. And this is the first occurrence of such hints that this can be done, and this is true. We will later learn what quantity is exactly determining this effect. Good. So that was the heuristic approach. And then now let's see what would be a better or an exact explanation of this. And for doing this, we separate our radiation impedance in the real and imaginary parts. It would be the case here. So now we have a real denominator and have the real and complex part of the denominator. And the power that is introduced into this system corresponds to that's the real part of the velocity product, and here the pressure is replaced by the radiation impedance times the velocity, and we would get this expression here, where we have the velocity expression here at the end. So it's a sinus hyperbolicus and some other expressions here. And once we assume a very high frequency, we can find approximative expression for all those expressions here. That means this is no longer valid, because this is hidden by the very high values of those expression. And for upper limits, the result is like this. So from the asymptotic treatment, we have now proven that our tube, even if there is a rigid end, behaves as if it would have been the power introduced in an infinite tube without any reflection. Again, proving this semi-infinite system replacement that is valid in SEA subsystems. So again, the heuristic approach is the absence of refraction due to damping means that the tube equals radiation into the free field, semi-free field. Good. Okay. So numerically, that means that the radiation impedance of our tube, which is this one here, equals the characteristic impedance for high frequencies. Okay, so far for the power introduction properties and some other things. Now we come to another property that's very important because it is a measure for the complexity of our system. And we come back to the idea of modes. In the first sections, we have described modes as a solution of masses and spring systems, but the same can also be done for a continuous system. Logically, the mode shape follow from that we have a wave equation, and very important, we need boundaries. If there is no boundary, you will not be able to describe or find modes in such systems. If we have boundaries, here we assume that we have rigid ends, so the velocity is 0 at 0, x equals 0, and x equal to the length of the tube. We would get this result for the velocity, and the same, something similar would be the case here for the velocity at Lx, and from this we can identify various solutions of A and B, which would look like the thing before. First of all, it must be equal. And if we enter this into the second result, we get the following mode shapes. It is, surprise, surprise, a cosine function of the pressure, or it is a sine function in velocity. And the wave number that fits into this is a typical means that the wave number equal integer number of pi divided by the length of the tube. Typical values are given here, so this would be a half wave length fitting in the tube. That would be a full wave number, and so on and so on. So on top of that, you will have an n equal to 0. That's an existing mode. It does not exist in spring mass systems, but in a cavity system or in a tube system, this corresponds to the static pressure, which should normally also be considered. Good. So the wave number could also correspond exactly to modal frequency, and the modal frequency would be like this, and the wave number corresponding to all the modal frequency would be like this. The wavelength, sorry, not the wave number, the wavelength. Good. So, so this is the normal classical solution. Why do we need those modes? Yeah, it could also be used to use a modal solution or to make a transformation into a modal system. But here in our context, it's much better to understand when we excite such a system by broadband signal, as it was shown in the statistical excitation chapter. We learned that the more modes are in our band, the higher the probability to excite all of the modes. That's an important quantity in SEA. And to calculate this modal system, we first of all start with a mode count. This is simply the number of modes that you have until a specific frequency. In our one-dimensional case, that's quite easy because you're just counting them on the frequency axis, and then you make a cut maybe here. And then you can definitely easily count all the modes that are below this frequency. But much more important is the number of modes that you find in a specific band. And this is the so-called modal density. So that's the number of modes in a specific band. And if you do the limit process for small limits, it would be the derivative of the mode count divided by with respect to the angular frequency. For our one-dimensional case, that's an easy thing because we have a simple formula for our mode count, just taking the delta omega, which is the distance between all the different modes, and if we take the derivative with respect to omega, we will get this expression. So this is the very important formula for the modal density of one-dimensional system. It could be other systems like bars and whatever. The formula, the general formula would look the same, more or less. Good. Again, why do we need this modal density? It is an indicator for dynamic complexity. So the more modes we have in one frequency band, the more complex is our system. And also a high number of modes in one specific band says, okay, we have a very complex system, and also we might have a system that can only be or should be described by the SEA approach. Good. And coming from the excitation field, the more modes we have in one band, the easier they can be excited in a specific bandwidth. So far for the one-dimensional fluid systems. And in the next session, we will talk. I would like to talk about another system that would be much more. It would be cavities. This is an important thing. Why is that? Because cavities or rooms are something like the mother of or the first creation of SEA. Because some of you are familiar with diffuse field theory, with reverberant rooms, etc., etc., and that's something where the first time a statistical description of wave field was introduced, long before SEA was created. And the reason is that cavities are excellent statistical subsystems because they are large, you have a relatively small wave number, and the dimension is high. And you will learn in session number 13 why this is the case. Have fun and see you later.